In Rust, we have safe pointers with borrowing rules that catch these bugs at compile time. Checked for safety at compile time, compile time, compile time, compile time, compile time, compile time, constructed at compile time, compile time. We'd prefer to find our bugs at compile time rather than at runtime. Our question today comes from Furry Onko, who asks, can anyone explain what does at compile time even mean? It sounds intuitive, but I don't understand shit for real. Furry, thank you for your question, and it's a completely reasonable thing to ask. If you're coming from a language like JavaScript or Python, there is no separate step where you compile your program before running it. And this is exactly where a lot of Rust's benefits turn up. So let's get really clear on what's going on. And yes, I did say the next video would be about generics, but when I sat down to write the script, I realized I need to answer this question first. Before we get into a discussion about monomorphization, you need a clear picture of what is in an executable program and how it gets there. So ultimately, no matter what language you're writing in, the thing that executes your program is the CPU. The CPU is the hardware, the big mess of transistors on a chip that implements a particular instruction set. That instruction set might be x86 or ARM or something else, and those instructions have a fixed binary format. So for example, this is my copy of the Advanced RISC Machines Architecture Reference Manual, better known as the ARM. This documents the ARM instruction set, and flipping through it you can see the various instructions and their binary formats. This one is from 1996, so it's all 32-bit stuff. And yes, I was writing ARM assembler in 1996. I'm old. Newer versions of the ARM architecture don't quite fit in a book of this size anymore, but it's the same idea. An executable program is a file containing instructions that can be loaded into memory. When your program runs, the CPU fetches the instructions from memory and executes them. Now, if you were really dedicated, you could craft an executable file by hand. You could look up the binary encoding for each instruction and enter it all with a hex editor. Back in the day, you'd be flipping switches or punching holes in paper cards and entering your program that way. And no, I never did that. I'm not that old. Nobody does that anymore. We use programming languages that are much more human readable. And for now, I'm just talking about compiled languages like Rust, C, C++, and there are plenty of others. The source code that you write in a text editor is the input to the compiler that produces the binary executable. When we say at compile time, that's what we're talking about. It's what happens when you run cargo build. If you're running a program in the playground or you're using cargo run, you don't really see it happen as a separate step because it's automatically running the compiler and then immediately executing the resulting program. But it's there. These are two separate steps. In fact, let's take a closer look. If I run cargo new, I get a new Rust project with a default Hello World program. When I say cargo build, that creates a target directory, and in there is a debug directory. It's called that because by default, cargo builds an executable that's intended for debugging my program. This directory contains a bunch of stuff, but the thing I want is the executable. It's this file called hello. And when I run it, it prints hello world. This file is the compiled program. I could delete everything else in the directory, the source code, I could delete the compiler, and this program will still run. All I need is this one file, and I could move it anywhere on the system. It doesn't care what directory it's in. So what's in this file? Well, it's not a text file, it's a binary format, so we can break out hexdump to take a look. And yep, those sure are bytes. Something here about page 0 text. Those bytes at the start look interesting. There's a tool that's pretty good at guessing the format of a file based on the first few bytes, and it's called file. That tells us this is a Mark O 64-bit executable ARM64. Cool, now we're getting somewhere. Yes, this is an executable and I'm on a Mac, so it makes sense I'm using the ARM64 instruction set. Now that we know this is a Mark O binary, then of course we can disassemble it with objdump -mxdr. That's just obvious, right? So now we're looking at the instructions in the program. So for example, this sub instruction subtracts hex 20 from the stack pointer SP. This BL instruction is branch and link. It calls another function. This ret instruction returns from the current function. So this dozen or so instructions are what the compiler spat out to implement a function. and the name of the function is this long messy string at the top. That name comes from something called symbol mangling, and there's a tool we can use to demangle it. It's called rustfilt, and we can install it with Cargo. So now I can pipe the disassembled code through rustfilt, and we get much more readable names for the functions. There's a lot of boilerplate stuff in here to do with program startup. The function I actually want to see is the main function from our Hello World program. And searching for main, here it is. This one in the namespace of the Hello crate is the one that actually prints Hello World. This other main function is more program startup stuff. So now we can see what we got from compiling the println macro. There's a call to arguments from strua followed by a call to stdio print. Makes sense. Another way to see what the compiler spits out is in the Rust playground. Next to the button that runs the program, you can expand this menu and you get this option to look at the assembly code. The compiler goes through several layers of transformation with different intermediate representations before it eventually turns your program into binary instructions. So there are options here to see what it looks like at each of those stages, and it's pretty interesting. So now you know what's in an executable program. The point of a programming language is to make it much easier to make programs that do what we want them to do. In source code, the program is represented in a way that's easier for us humans to understand. The compiler removes a lot of laborious repetition, turning that into something the machine can execute, and importantly, sometimes the compiler can tell us if we're trying to do something that doesn't make sense. If the language is designed so the compiler can check things for us, then when we make mistakes, we get helpful compile errors, and that's a whole lot better than having a program that seems fine as far as the compiler is concerned. It passes the checks, it seems to run, but then one day it hits some input that causes it to crash. Or even worse, an attacker finds a way to craft some input that causes the program to do something it really should not do. If you're working in a language like C or C++, it's quite easy to accidentally write code that can corrupt the memory of the running program. The language doesn't provide enough information for the compiler to be able to tell whether you meant to do that or not, so it happily compiles, and then with the right input it can blow up at runtime. Memory corruption bugs provide great opportunities for attackers. So this is an area where Rust is really strong because it guarantees that a program with memory corruption bugs will not compile. And like I keep saying, we'd prefer to find our bugs at compile time rather than at runtime. Now, at this point, I can hear you jumping out of your chair, shouting at me, "Ben, a moment ago you said Rust is safe. Now you're saying safe Rust is safe and unsafe Rust is unsafe. The second I need to do anything with pointers, I'm in unsafe Rust and all bets are off. How's this any better than C?" Okay, slow down. The practicality of using Rust is that you almost never need to use unsafe Rust, and that is because safe Rust has safe pointer types. These pointers are called borrowed references, and they come with zero runtime overhead.